In this video, we will discuss about mass moment of inertia. It measures resistance of a body to angular acceleration. Means if we apply the force or a torque for angular acceleration, then how much body will resist it, means how slowly it will move for a particular amount of mass. So it shows a resistance. Like area moment of inertia, it shows to bending moment. And here mass moment of inertia shows resistance to angular acceleration. It measures how much mass is away from the rotational axis. Like if there is a mass kept here and it is rotating with this axis, then how much away it is kept. So more far from the axis of rotation, more will be the moment of inertia. So here if you see, there is a mass m, resistance r from this rotational axis. So mass is rotating with this axis. Now if you want to calculate inertia for this axis, then I will be equal to mass times the distance square. So I equal to mr square. That will be inertia in this direction with respect to this particular axis. Now there are two theorems, parallel axis theorem and perpendicular axis theorem. So in parallel axis theorem, if you want to calculate inertia for any other axis, and for one axis you know the inertia, let's say you know ixx here, which is mr square. You want to calculate inertia with this axis here. Imagine one axis here, and this axis is at a distance of d from this axis. So you can simply calculate Iy will be equal to Ix, which you already know, plus mass of this object times distance square between these two axes. So this is how you can calculate inertia for any other axis if one axis is known and the distance between two axes is known. Perpendicular axis theorem is, if you know this Ixx and perpendicular direction Iyy, one is horizontal, one is vertical. So if you know both these inertias for a particular mass, then axis perpendicular to both these axes means the perpendicular axis to the plane of this paper, you can directly know which will be equal to Ixx plus Iyy. So Izz will be equal to Ixx plus Iyy. So this is how perpendicular axis theorem you can find inertia in direction where two inertias are known which are perpendicular to this direction. So these are the two theorems, and we will see some common objects for and standard formula of inertia. So this is a slender rod. It's a long rod where radius is negligible. Now to calculate inertia Ixx, it is simply ml square by 12, where L is a length, m is the mass of this rod. If you want to calculate inertia with respect to this axis, and the object is rotating with respect to this axis, so object is going inside the paper and coming out from the other side, and it is rotating like this. So now Iyy will be simply, we can calculate from parallel axis theorem, which will be Ixx. We already know Ixx plus mass of this mass m and distance is L by 2 square. So Ixx plus m L by 2 whole square, this will be Iy. So for this axis inertia will be this, which if we put this value here, ml square by 12 in at place of Ix, we can get ml square by 3. Now for disc, this is a simple disc of small thickness, then mass is m and radius is r. So if you want to calculate for any diametral axis, then it will be mr square by 4. But if you want to calculate the axis which is perpendicular to this paper, means Iz, then it is mr square by 2. From this theorem, that Ixx plus Iy means it will be 2 times. Iz will be 2 times of Ix and Iy. So Ix and Iy will be same because it's a symmetrical circular disc. So any axis will be same as xx. So here mr square by 2 into 2 will be mr square by 4 into 2 is equal to mr square by 2. Now if you want to calculate for very thin ring where thickness is negligible compared to radius, so it's a thin ring. So Ix will be mr square by 2, and Iz, because each and every, if you take any dr length or any small particular element here, it will be having simple mr square. So for entire mass, the Iz with respect to this particular perpendicular axis will be mr square, and Ix will be half of that mr square by 2 from this perpendicular axis theorem. So this is how we can calculate for very thin ring, because mass is at equal distance from this z axis which is coming out of the paper. So like this we can calculate for Iz, and for Ix we have to simply divide by 2. For sphere, all three axes will be same, Ix, Iy and Iz, because it is symmetrical for all the axes. It will be simple 2 by 5 mr square. For hollow sphere, same situation, all three axes is same, but moment of inertia will be increased because m will be distributed far from the center. Here entire m is distributed inside the sphere, and here entire m is distributed at the hollow sphere is there, so very thin sphere we can assume, so at a distance. So 2 by 3 mr square, this is actually for thin sphere, 2 by 3 mr square. R is a radius of the sphere. Cylinder, this is a cylinder with radius r and length l. So if we want to calculate inertia with central axis Iy, which is cutting equally into two half, so here Iy will be equal to this, but Ix, this is a horizontal axis. So for horizontal axis it is mr square by 2, same as disk, because we can imagine it is made up of multiple disks, and all the disks will be adding m1 r square by 2, m2 r square by 2. So if we take out r square by 2, then m1 plus m2 plus m3 will be equal to m only. So this is same as thin disk. And if you want to calculate for Iy, it will be ml square by 12 plus mr square by 4. So this is for particular this axis. This and this case, cylinder and cylinder rod are different because here r is negligible, but here we have to calculate separately for r also, mr square by 4. Like if you see here ml square by 12 is there, we have to neglect for the radius, and here we have to neglect for the length because it's a thin ring, thin disc. So if you want to calculate for Iyy, which is here Iyy and here Ixx are same, so ml square by 12 for cylinder rod, and for radius we have to get mr square by 4. So these two will combine, give the effect of this cylinder, because this disc and length both effect, here thickness we are neglecting in disc, here radius we are neglecting, but if we combine both this, then we have to, for Ixx we have to get both this. So here Ixx is actually Iyy. If you see here Ixx is central, here Iyy I have mentioned. So Iyy will be ml square by 12 plus mr square by 4. And the last two are hollow cylinder. This was the thin solid cylinder. This is a hollow cylinder. So here mass is distributed in the entire cylinder, but here mass m is distributed for this hollow cylinder. So we are not cutting the section out, actually this entire mass we are redistributing over this entire hollow cylinder. So here Iz, which is from the center, it is m by 2 r1 square plus r2 square. This is slab having some thickness and length b and width a. So here a and b are length and width of the object, and it's a slab. So for this z axis passing through the center, we have m by 12 a square plus b square. These both are almost similar. Here radiuses are there and here length and breadth are there, but here we have to divide by 2, here we have to divide by 12. And for I corner, for any corner axis, this axis which is passing through the corner, if you want to calculate, then we can apply this parallel axis theorem. We already know for the central axis, so Ix is Iz here. So for I corner, Iy, which is I corner, Ix we already know, which is Iz here, which is this value. we have to add mass plus distance square. So mass m of this slab plus distance from between both of these axes, that will be d distance. We can also calculate from geometry a and b. This is a by 2 distance, this is b by 2 distance, and we apply Pythagoras. So here plus m into d square. So this is how we can calculate for corner. So these are some important formulas for different shapes, and we can also subtract and add different moment of inertia for mass also, same as area also. And thank you for watching this video. See you in the next video.